Today we're looking at rates of change of polar functions. So we're going to begin with something that we have already done in the past with functions in the xy plane, Cartesian coordinate system. We're going to talk about average rate of change. Again, we did this first thing in Unit 1 way back in August. And it's popped up on a couple of different tests. This is an important topic that we consider in calculus as well. Average rate of change. We have an abbreviation for it called AROC. So average rate of change is always, I think of it as change in y over change in x. Average rate of change. Slope. Slope between 2 points. Okay? We're finding the average rate of change of a polar function. We do it the same way. They tell us we want the average rate of change of g with respect to theta. So I am finding delta g over delta theta. They give me the two theta values. So I like to put the larger one first here, minus the smaller one on the bottom there. And on top I need g at 4 pi over 3. I don't know why I'm writing so tiny here, but oh well. Minus g of pi over 3. So I'm going to go off to the side and get g of 4 pi over 3 and g of pi over 3. For the 4 pi over 3, I'm going to my g definition. 6 times cosine of 4 pi over 3, that's a negative 1/2, third quadrant, right? So this is negative 3 minus 5, that's a negative 8. For pi over 3, 6 times cosine of pi over 3 is 1/2. That's 3 minus 5, that's a negative 2. I'm going to go put those values up into our AROC equation. Negative 8 minus a negative 2. 4 pi over 3 minus pi over 3 is 3 pi over 3, which is just pi. So this is negative 6 over pi. That's the average rate of change of g with respect to theta. Okay? If g had units of centimeters, what would be the units for that average rate of change? So we have delta g over delta theta, right? So I take units of g, which are centimeters, and I divide by units of theta, which in this course and in calculus are always in radians. We do not touch degrees in either pre-cal or calculus. So if there's a theta, it's going to be in radians. Okay? Centimeters per radian. That would be the units. We can use the average rate of change to approximate a value of a function. So I have a little flashback to what we did in the past with this. This is not polars, this is just x's and y's. Okay? It says f is a continuous function, selected values are given in the table. Use the average rate of change of f on the interval, this should be a negative 2, on the interval from negative 3 to negative 2 to approximate the value of f of negative 2.5. Okay, so I start by finding the average rate of change. If we have to use the average rate of change, we have to find it first, right? So I'm going to find the average rate of change. That will be change in f over change in x from negative 3 to negative 2. So that will be f of negative 2 minus f of negative 3 divided by negative 2 minus a negative 3. So plus 3 on the bottom. F of negative 2 from the table, f of negative 2 is negative 1. F of negative 3 is 5. We're dividing by 1, so the average rate of change is negative 6. That is the slope between those 2 points. Now we're going to use that slope with one of those 2 points. One of those 2 points, it does not matter which one at all. One of those 2 points and the slope to get an approximation for the f of negative 2.5. So the point that I'm going to use, I like to use the leftmost point. So I'm going to use negative 3 and 5. Negative 3 and 5. I think of this as x1, y1. Okay? And I'm using my slope, which we just found. Okay? And we're going to get our new point. Our new point will be x2, y2. And I know the x-coordinate of our new point. It's negative 2.5. Okay? The y-coordinate is what I'm looking for. So I'm using the point-slope form of the equation of a line. That is y2 minus y1 is equal to the slope times x2 minus x1. Okay? So y2 is what I'm looking for. I'm going to call that just a plain y. That's what I'm looking for. Minus y1 is equal to the slope times x2 minus x1. And now I just have to solve that for y. So y minus 5 is equal to, this is negative 6 times a half. And negative 6 times a half is negative 3. Add the 5 to both sides, and we get that y is 2. That means that f of negative 2.5 is approximately 2. It's only an approximation. We have no idea of how accurate it is. It's an approximation. Okay, we're going to do the same thing now with polars. The exact same process, but with polars. Okay? All right. So we have this function h. They didn't give us a table this time. They gave us the function. We are approximating h of 5 pi over 12 using the average rate of change on this interval. So 5 pi over 12 is between pi over 3 and pi over 2. So we're going to use the average rate of change on that interval to approximate the y-coordinate at 5 pi over 12. So first thing I do is I find my average rate of change. So delta h over delta theta. H of pi over 2 minus h of pi over 3 divided by pi over 2 minus pi over 3. For h of pi over 2, I'll come off to the side and find that. And h of pi over 3. H of pi over 2 is going to be 2 plus cosine of pi over 2 is 0. So h of pi over 2 is just 2. H of pi over 3 is 2 plus cosine of pi over 3 is 1/2. So that is 5/2. So h of pi over 3 is 5/2, like that, divided by pi over 2 minus pi over 3. I'm going to multiply top and bottom by something that will reduce a 2 and a 3. So I'm going to multiply top and bottom by 6 because that will get rid of all of the little denominators there. And remember that we are distributing that 6 through everything. So 6 times 2 is 12 minus the 2 and the 6 here will reduce to 3, so we have a 15 there. 6 times pi over 2 is, the 2 reduces with the 6, leaving a 3. 3 reduces with 6, leaving a 2. So this is negative 3 divided by pi. So I think of that as the slope. Think of that as the slope. Okay? Now, we're going to use one of the points and the slope to get our new point. Okay, so our points my starting point. I think I'm going to use the pi over, well, it doesn't matter. We can use either one, truly. I usually use the smaller one, but we could use the larger one. I might like to use the larger one because its y value is just more pleasant than the 5/2. So I think you know what? No, I'm going to use a smaller value. I'm going to be really consistent and always use the smaller value. So I'm using the smaller angle, and its y coordinate is 5/2. So keep in mind, we're going to the point with x coordinate or theta coordinate, 5 pi over 12. And this is what we're looking for. This is what we're going to approximate using that slope. So y2 minus y1 is equal to the slope times x2 minus x1. Okay, where this is my x1, y1, this is my x2, y2, but I'm just going to call that a y here. So y minus the y coordinate of the other point is equal to the slope times x2 minus x1. So we're going to clean this up. Okay, when I distribute this into each piece here, for this first piece, the pi's would reduce out, and the 3 and the 12 also reduce, leaving a 4 in the bottom. It's going to be a negative 5 over 4. The pi's are gone. For this next one, a negative times a negative is a positive. The pi's reduce and the 3's reduce, leaving just a 1. So we have y is equal to, I'm adding my 5/2 to the other side. I'm going to get a common denominator. I need to multiply the 5 and the 2 by 2 to get, oops, I said 5 and I wrote 5. 10/4 is 5/2, right? Minus 5 over 4 plus 4 over 4. And that's going to give me 9 over 4. So our approximation for h of 5 pi over 12 is 9 over 4. Okay, this was a multiple choice question that I saw on AP Classroom. This is the way they asked it. Okay, the table of values gives of a polar function is given for selected values of theta. If the value of f of pi over 12 is estimated using the average rate of change over this interval, which of the following is true? So they gave us pi over 12, the value of pi over 12. They gave us that it is 1/2. They're asking us, is the estimation, is the approximation that you can find bigger or less than the 1/2? So we have to go ahead and find the average rate of change and use it to approximate f of pi over 12. Okay, so first I'm going to find the average rate of change. I accidentally put an h from the previous problem. That's an f. So f of pi over 6 minus f of 0 over pi over 6 minus 0. They gave us these values in the chart. We don't have to go find them. F of pi over 6 is 7 over 8. F of 0 is 1/4. And then we have a pi over 6 in the bottom. I'm going to multiply top and bottom by a 24 because a 24 will reduce an 8, a 4, and a 6. And I just need to be careful to distribute that. So 24, 8 goes into 24 3 times, and 3 times 7 is 21, minus 4 goes into 24 6 times. 6 times 1 is 6. And 6 goes into 24 4 times, so we get 4 pi. So this is 15 over 4 pi. So I found my slope, my average rate of change. Okay? And now I'm going to use that to approximate f of pi over 12. So we need our points, x1, y1. I'm going to use my smallest one here. So I'm going to use 0, 1/4. And we're going to pi over 12, and then we're looking for the y coordinate there, right? This is x2, y2, but I'm just going to call it y when I'm working it out. And the slope is there. So again, I'm using y2 minus y1 is equal to the slope times x2 minus x1. Okay? So y, that's what I'm looking for, minus y1 is equal to the slope times x2, minus x1. All right. Let's distribute this. Fortunately, there's a 0 there, so we can ignore that. The pi's reduce. And 15 and 12 have a common 3, so that's going to leave me a 5 and a 4 in the bottom. So that's going to be pi over 16. So add the 1/4 to the other side. Get a common denominator of 16. 1/4 is 4 over 16. Like that. Oh my gosh, never mind. Goodness gracious, the pi is reduced out. It's not a pi, it's a 1 there. Goodness gracious. Okay, so when we get a common denominator, okay, is 16, so that's 4 plus 5. I am making mistakes right and left. That's a 5, right? 4 plus 5. Goodness gracious. So 9 over 16 is our approximation. F of pi over 12 is approximately 9 over 16. But in the table, we know f of pi over 12 is a half. So is this higher? Is this an overestimate or is it an underestimate? Well, it is 1/16 higher, right? So it's an overestimate by 1/16. It's a long problem, right? Okay, on to something a little different. Relative extrema of polar functions. So relative extrema, let's think back to what we did in the past. How many relative maxes does this function have? A relative max are the high humps, So there are 3 of those. How many relative mins? Those are the low humps. So there are 3 of those. So how many relative extrema are there? Extrema means both mins and maxes. So there would be 6 of those, right? Points of inflection. Let's remember what points of inflection are while we're here, just to review that. A point of inflection is a point where concavity changes from concave up to concave down or concave down to concave up. So I'm looking for where does it change from concave up to concave down or concave down to concave up. I see one around that spot. I see one around this spot, and this spot, and this spot, and that spot. So it's around there. How many are there? There are 5. Okay, for polar curves, Here's our definition for relative extrema of a polar function. For a polar function, if the function changes from increasing, so if r changes from increasing to decreasing or decreasing to increasing on an interval, then the function has a relative extremum on that interval. And it corresponds to a point that is closest to or farthest from the origin. Okay? So, where r is changing from increasing, here I think of r as changing from increasing to decreasing. So on a rose, the relative extrema will be at the tips of the petals. So those would be the relative extremum for that polar function. There are 4 of them, the tips of all the petals. So how many relative extrema does this function have? Well, this is a rose with 7 petals. So there must be 7 relative extremum. 1 per petal. Easy peasy. Okay. I saw a couple of AP questions like that too. All right. For this polar function, let's determine all the values of theta between 0 and 2 pi where there is a relative extremum. Okay. This is an 8-petaled rose. So we're going to have 8 relative extrema, which means we're going to have 8 values of theta for our answer. Okay? So let's visualize what we're dealing with here. It's a sine rose with even petals, 8 of them, so the petals are in each of these inside each of these quadrants, not on any axis. Draw on these petals. Okay? And these are going to be, we need those theta values. So let's find those theta values. So at the tips of the petals, each petal is of length 6, true? Each petal is of length 6, which means that this is r equals 6 or negative 6, right? Each of these is 6 or negative 6, right? So I'm going to take my function and, oh my gosh, I'm going to take my function and set it equal to positive or negative 6. If we divide both sides by 6, we get sine of 4 theta is positive or negative 1. So what angle makes sine positive or negative 1? That angle would be pi over 2 or 3 pi over 2 between 0 and 2 pi. We have a 4 theta. That's our angle, right? Since there's a 4 here, I'm going to multiply the number of these between 0 and 2 pi by 4. So I'm adding 2 pi to each of these. Add 2 pi and we get 5 pi over 2. Add 2 pi and we get 7 pi over 2. You can see the pattern here. What would be the next one? 9 pi over 2, 11 pi over 2, 13 pi over 2, 15 pi over 2, and we could keep on going, right? But I'm going to stop there, because if we multiply both sides by 1/4 to get theta by itself, those are the only ones, once I multiply through by 1/4, those are the only ones that will be before 2 pi. Plus, I knew there would be 8 answers, and this is going to give me all my 8 answers. So I'm multiplying pi over 2 times a fourth. That'll be pi over 8. This will be 3 pi over 8, 5 pi over 8, 7 pi over 8, 9 pi over 8, 11 pi over 8, 13 pi over 8, and 15 pi over 8. Notice that that is less than 2 pi. So these are my values of theta where my petal tips lie. Which of the following is false? Which of the following is false? Okay. If R is positive and increasing, think about that. If we are here, if we're at theta is 0 and R is, let's say that R is 4 here. If R is increasing, that means maybe the next R would be R is 5. If R is increasing, if R is positive and increasing, what is the distance from the origin doing? If R is positive and increasing, R positive and increasing, the distance must be increasing. The distance is increasing. What if R is positive and decreasing? So what if R started at 4, but then the next one was R is 3? Then what is the distance between the curve and the origin doing? The distance here would be decreasing. I think of this as a positive, and increasing, I also think of that as positive. And I think two positives make a positive. This is positive, but a negative. A positive and a negative make a negative. Okay? I think of it in that way. Okay, what if R is negative? What if R at theta is 0 is a negative 4? R is negative 4. Gosh, negative 4. But it's increasing. That means the next R maybe would be negative 3. What's the distance doing? The distance is decreasing. If R is negative and increasing, the distance would be decreasing. I think of that as negative and positive. They make a negative, decreasing. What if R is negative and decreasing? It would go to negative 5 rather than negative 3. That distance is back to increasing, right? Negative and decreasing, the distance would be increasing. Okay? So what is the one that's not true? That's true. That's true. This one is false. So that answer would be C. Okay. This topic was rates of change of polar functions.